Hi, this is Jeff from the Ozark Mountains. That's in Missouri in the USA. It's been an absolute age since I did a video about programming, so I thought we would take a look at how DIGIs were created and played on the Commodore 64. You might be saying, hey Bert, what the heck is a DIGI? Well, that's a darn good question. I'm glad you asked. You might remember the digitized speech from programs such as Ghostbusters, and Impossible Mission.
Another visitor. Stay a while. Stay forever.
While that may not seem that impressive today, back in the day, that was mind-blowing. Since all of this would wind up making one very long video, I thought we would break it into two parts. In part one, we'll learn a little bit about sound, how we'll record our sound and process it and crunch it up to fit on a Commodore 64, and we'll learn a little bit about the Digi player on the Commodore 64 itself. We'll finish up part one by taking a look at how the iconic Digis and programs such as Ghostbusters and Impossible Mission were created by a physics professor. In part two, we'll go into the software involved in fine detail. This includes the Cruncher program, which takes your recorded sound and packages it and processes it into a format that a Digi player can handle, as well as the Digi player itself and some variants for playing compressed files. Well, let's jump right in. First, I want to thank Robin from the 8-Bit Show and Tell channel. I first got interested in learning how Digis work around January of this year, in 2020 that is, and one of the first pieces of information I found was an article he helped write back in the day. He was gracious enough to let me bug him with lots of questions. A link to his channel is in the description below. You probably remember from science class that sound is just vibrations carried through the air. A physical object vibrates, which causes the air around it to vibrate, and that vibration is carried through the air all the way to your ears. This means, and I hate to be the one to break it to you, that all those loud explosions of spaceships and stuff from your favorite sci-fi movies, yeah, that's all fake. Space is a vacuum, or darn near it. There's no air or other gases to speak of, thus no vibrations carried through the air or other gases, thus no sounds, and no big explosions. I know, we're all a little let down after a lifetime invested in watching sci-fi. To get an idea of how sound is reproduced, let's take a look at a speaker. The basic idea is that there is a coil which makes up an electromagnet, number 2 in this picture, connected to the speaker cone. And there's a permanent magnet mounted on the speaker frame, which is number 1. The electromagnet is energized in proportion to the sound being reproduced. As the coil is energized, the cone is drawn closer to or repelled away from the resting position. If we were able to look at a speaker cone in super slow motion, we would see it moving in and out very quickly. The faster it moves in and out, the higher frequency of sound it makes. The further it moves in and out, the louder it appears to be. If we were able to measure the position of the speaker cone as it moved, say once a second, and we wrote down the value, we would have digitally recorded the sound. We would have a single number from each point in time that describes the speaker displacement. We're showing this here when the speaker is at A, that's the resting position, B is at extended 1 unit, and C, it's retracted 1 unit. And we can visualize the speaker movement with some awesome stop-action animation. Recording the position of the speaker once a second is not very useful. We would really need to do so thousands of times a second. The more times we can measure the sound every second, the more realistic our reproduction of sound will be. The rate at which we would need to sample a certain frequency in order to reproduce it is called the Nyquist value. Basically, we need to sample at twice the frequency of the highest pitch we want to reproduce. The gritty details are outside the scope of this video, but I encourage you to do some searching on the internet if it's of interest to you. The big idea here is that we can reproduce the sound by recording one number, which we are calling the position of the speaker. This is a signed number describing how far the speaker cone is moving in or out from its resting position, that is, plus or minus the resting position, which we're calling 0. The SID chip in our beloved Commodore 64s have a bug. Well, they have more than one, but the one we're interested in today is the volume bug. When you change the volume level on the C64, it makes a popping sound. Let's have a look. Here we just have a simple basic program which changes the volume register on the SID chip to 0, and then it changes it to 15, which is the maximum volume. Now when I run this, you'll hear a pop. Let's try that one more time. The audio output on the SID chip has a DC offset voltage. When you change the volume, you also change the offset voltage, and this change in voltage produces a sound. So how do we get speech from this popping sound? Let's think back to what we learned about how a speaker works. It moves in and out. The faster it moves in and out, the higher frequency of the sound it makes, and the further it moves in and out, the louder the sound. So by adjusting our SID volume, we get a popping sound, and if we do that really quickly, we can make a tone. If we can control how fast it changes, we can control the tone. If we also control the magnitude of the volume changes, it would be like controlling how far a speaker moves or how loud the sound is. You might be thinking, hey Bert, that's a great theory, but how do we actually do that? Well, that's a good question. I'm glad you asked. The first thing we need to do is get our sound sample into a format and memory footprint that our C64 can handle. To this end, we're going to use a free program called Audacity to record and process our sounds. The first step is to record the sound, of course. The less noise in your recording, the better, and since our C64 has a limited memory capacity, try to limit it to just a few seconds. So let's record something. Hey Bert! The rate at which we can play back sounds on the C64 is limited, so we need to do some processing and filtering on what we just recorded. First, we want to convert the sample to mono. We do this by clicking on the arrow next to Audio Track, and then click on Split Stereo to Mono. Then we can delete one channel by clicking on the X at the top left corner. This leaves us with just one channel of audio to worry about. Now we'll trim out all the silence on each end of our sample by highlighting it and pressing delete. Just like that. Then we need to limit its frequency range with some filtering to match the range which we can play back on the C64. This will improve how it sounds. The DIGI player we'll look at later runs at 8 kHz, so we need to create a low-pass filter to allow only the audio frequencies 4 kHz and below. Remember the Nyquist value we talked about? We need the sample frequency to be at least twice as high as the highest audio frequency we wish to reproduce. We can apply these filters by selecting our whole track by clicking in the track, doing a Control-A, going to Effect. We'll go down here first and select a low-pass filter, and this is where we would say we want everything 4 kHz and below. Then we would do a high-pass filter and say we want everything 300 Hz and above. And the last thing we'd want to do is normalize our sample, which allows us to take up the entire vertical range that's possible. This way we have the highest resolution from our output. Some of you may recognize that this combination of a high-pass and a low-pass filter is a bandpass filter. I'm using separate filter settings here for clarity, but you could configure a bandpass filter to do the same thing. I created a macro to perform the filtering and normalization in one step. To use the macro, you just press Tools, Apply Macro, and select C64 DIGI. Notice how our waveform is now taking up more of the vertical range, and if we play it, hey Bert, it sounds a little tinnier. After we're done with our filtering and processing, we need to save the sample out in a simple format to make it easier for some additional external processing. The first thing we'll need to do is set our project rate to 8 kHz. Then we're going to go up to File, Export, Export Audio, And we want to make sure we're saving as other uncompressed files, as a raw headerless file, and we want the encoding to be signed 8-bit PCM. And then we click Save. This gives us a file with values ranging from +127 to -128, and then we'll use a homebrew bit of code to further process this file into something the C64 can handle. What I've covered here is just the basic processing settings needed in Audacity. It's entirely possible to improve the quality of the finished product even more by doing further processing with Audacity. I leave this to others who know more about sound processing than I do. What we've done up to this point is record some really good quality audio at a 44 kHz rate, and it's saved in a 32-bit floating point format. Then we did some processing and filtering on that and exported it at an 8 kHz rate in an 8-bit signed format, so we greatly reduced the quality. Coming up next, we're going to use a custom cruncher program to convert that data to an unsigned format and make sure it's scaled from 0 to 255, so we'll have an 8-bit value. Then we're going to further reduce the quality by converting that to 4 bits so we can pack 2 samples per byte. So far, we've reduced our very good quality sound sample down to a smaller and lower quality version. This is still too high resolution for our poor old C64 though. The volume register on the C64 SID chip is only 4 bits wide, so we need to downsample from 8 bits to 4 bits while also converting from a signed, a plus or minus value format, to unsigned. Since we're only using 4 bits of each byte, that is just the low nibble, we can pack another sample into the upper nibble. This lets us reduce the memory required on the C64 by half, but it does increase the complexity of the DigiPlayer a little bit. This cruncher program was written in C#, and it takes our 8-bit signed sample file and gives us a packed 4-bit unsigned file. It will also pad the file so that it ends on a page boundary, as this simplifies the DigiPlayer on the C64. I wrote the cruncher program so I could easily test each stage of processing. After each stage of processing, it will save a file at that stage. For example, let's load the file that we just saved from Audacity. We click on number 1 file, and we select the raw file. It'll show us our path here, and it also reminds us up at the top that it should be a raw 8-bit signed at 8 kHz. Now this program is not perfect. It was just something I did for myself, so I'm sure it'll be very easy to crash it if you load in the wrong type of file. The next thing we'll want to do is click the scale button. So this tells us what it's doing. It's converting it from signed to a 0 to 255 value. So it calculates the scalar and the offset needed and it applies that. And it saved our file out with a _SCL appended to the file name. Now, to do the final crunching, we want to set this to 8 kHz, and I'll go over these other 2 4 kHz options in the next video and explain what all that's about, and also explain what the rounding value is about. And these auxiliary functions down here, just ignore those for the time being. At any rate, the next step to the process is to click on number 3, crunch the file. As you can see, it saved a new file, and it tells us that it was saved at an 8 kHz rate with a 2 for a rounding value. And it also tells us the particulars down here that it reduced the file size from 5294 bytes to 2816. Now, the output file size is padded, so it'll end on a 256 byte boundary, which makes our player much simpler. So that's all there is to the cruncher at this stage. So here I've opened up CBM Prj Studio, which I like using for developing for the Commodore 64. And you'll notice here that this says DigiPlayer Simple. This is for playing a non-compressed digi file. We'll go over the details of how this works and how the one that plays compressed files works in the next video. For now, I want to let you know how to load in the data that we just got out of Audacity and ran through the cruncher program into CBM Prj Studio so you can play it. So a file that's already been imported looks like this, and it's just a bunch of data. And on each end, it's marked with the starting address and 2 tags for data start and data stop. Now I've got a bunch over here on the left-hand side, which are different samples of me saying, destroy him, my robots, at an 8K sample rate with different settings on the Cruncher program. So you can enable those and rebuild and play it and see what the difference in sound is. For now, we'll close this, and I've created an empty file here with just the tags and the start address. And if we go to File, Import Binary File, we can select our file that we just got out of the Cruncher program there. And I like setting it to use 16 values per line. And you can see the rest of the settings here. This pops up this file, and if you just do Control A to select all, Control C to copy it, and then we'll just plug that right in there. And you can see this is a lot of very similar looking data, especially on the ends, which is a little bit of silence. And on the tail end, you're going to see a lot of whatever the last value was duplicated to get to a 256 byte boundary. And then I will save that, and I'm going to double check that the Haybert 2 is included in the project build. It is. And then I'm going to build it and run it, and this will automatically launch Vice so we can watch it run. And you might notice how terrible that sounds. It's barely intelligible. And you might wonder why and be kind of disappointed, and I was too when I started this, and that got me into studying what was happening more. And it has to do with how we are converting from the 8-bit output that we got from Audacity to the 4-bit. You know, we're basically chopping off the lower 4 bits, and if those are close to rolling over and making a change in the upper 4 bits, we're kind of throwing away all that data. So what we need to do is add a little higher rounding value. And I've already output that file from the Cruncher program, so we'll go ahead and try that out now. We're going here with a rounding value of 4 instead of the 2, which we originally tried. Same import settings. You might notice right away that we have a bunch of 6s on the end instead of 1s. So we'll see what difference that makes. Let's go ahead and build it. Hey, Bert. And you can see that sounded a lot better. It's not always going to be the same rounding settings or filtering settings for everything that you record. It requires quite a lot of trial and error to get it to sound just right. Hey, Bert. And that's not too bad. You are now armed with enough information to dig in and create your own DIGI files and play them back on your Commodore 64. Keep in mind that each second of audio takes up 4K of memory, so it's easy to try and overfill the C64. In the next episode, we'll go over the Cruncher program in detail and learn what makes it tick and some more about the compression methods that I tried to save memory space on the Commodore 64. We'll also dig into the DigiPlayer in detail and find out what makes it tick and what changes were needed to support the compression methods. To wrap up this episode, I thought we would take a look at how the digitized speech samples in games like Ghostbusters and Impossible Mission were done, and what makes them sound so great while also taking up so little memory. This is thanks to a clever encoding scheme invented by Forrest S. Mozer in the 1970s. He was a physicist at the University of California, Berkeley, who designed instrumentation that was flown on satellites. Dr. Mozer became curious about speech and what elements of speech we use to understand it. He first started by examining speech with an oscilloscope, and then built an apparatus with dozens of switches purchased from Radio Shack. He fed a distinct signal through each switch, and by turning them on in various combinations, he tried to reproduce some elements of speech. Dr. Mozer noticed that there was a lot of redundant information in speech, and developed an encoding method which could compress the amount of data by 50 to 100 times. Given the very high price of memory at the time, this was a big breakthrough. Additionally, very little computing power was needed to decode the sample sound, so it was relatively inexpensive to implement. He received his first patent in 1974 for the technology. There are links below. He also did some very early work in speech recognition. The first commercial product which used speech synthesis was a talking calculator made by Telesensory Systems in 1975. Telesensory Systems made products for the blind and visually impaired. Dr. Mozer had a blind grad student at the time who used some of their products and introduced Mozer to the company. The Mozer technology was also later licensed to National Semiconductor, which they used to develop the Digitalker IC. His success in the endeavor led Mozer to found ESS, Electronic Speech Systems, in 1983. ESS was the company behind the speech synthesis used in more than a dozen video games. Mozer himself was the voice used for many of the first products, including the calculator and even video games like Ghostbusters, which were recorded and produced in a studio he built in his basement. Other voice actors provided the vocals for customers, like Disney's Mickey and Minnie Mouse. How did the Mozer compression system work then? Well, I'll put a link to a website below, as well as to the actual patents, and I'll try to explain what I understand about it here. Starting with a high-quality recording of the words they want to use, they then digitized the sound based on phonemes and reusing similar sound segments already digitized. This was a very manual process, taking a trained operator 50 hours or more to encode a vocabulary of 100 words. This encoding process reduced the initial 10 kHz sample rate down to 90 to 625 samples per second. On the Commodore 64, the sample rate is about 375 bytes per second, so a lot of speech can be packed into a little bit of memory. With this early technology, one had to learn to mispronounce certain words so they sounded correct when digitized. For example, you might say tree instead of three. These types of sounds are called fricatives. These are the sounds from letters like S, F, and TH, which are not modulated by your vocal cords. Rather, they are made by releasing breath through a partially closed passage, like between your tongue and your palate. While encoding was a very long and laborious process, playback was relatively simple. Simple operations like addition and table lookups were all that was required, so it could be accomplished by the simple 8-bit personal computers of the day, and even packaged into a single IC of that era. On the Commodore 64, the samples were played back using the same technique that we showed above, by quickly changing the volume of the SID chip. So, thanks to Dr. Mozer, a curious physicist, we got talking calculators, toys, video games, Coke machines, and even cash registers. And for me, having my Commodore 64 video game talk to me was simply mind-blowing. Thanks, Professor. Well, I hope you've enjoyed learning a little bit about DIGIs on the Commodore 64, how to record them, process them, and play them back. In the next episode, we'll go through the software involved in more detail and learn a little bit about the compression schemes I tried. I'm sure there are better compression schemes, but I'll show you what I did, and then you can come up with your own. We also learned a little bit about Forrest Mozer, who I think was an interesting guy. To be from a physics professor who built space instrumentation for satellites to just being curious about speech synthesis and really revolutionizing the industry, that's kind of amazing, I think. I think I would have liked to have been able to meet him. I'd also like to take a moment to say thanks to the folks who help support the Hey Bert channel through Patreon and other means. If you'd like to find out more information about that, just look in the description down below. Also, thanks to everyone who subscribes and watches the videos. If you'd like to subscribe, well, look down below for that rectangular box that says subscribe in it and click on that guy and then click on the bell-shaped icon so YouTube will be nice enough to let you know just as soon as I post a new video. Remember, come back next week where we're going to go over the software involved in the DigiPlayer creation and playing in more details. Well, until next time, bye.